We often use state diagrams, a type of graph, to represent problems. In this video for VCE Algorithmics, I'll go through a few examples and an exam question to highlight some things you might need to consider. The first is the wolf, cabbage, goat problem. A farmer needs to cross a river in a boat that can carry either a wolf, a cabbage, or a goat. If left alone, the wolf will eat the goat and the goat will eat the cabbage. First, we have to decide what each node will look like. Now let's look at a failed example here. If we have an array just showing the number of items on each side, why would this not be adequate? Well, because we need to know more than simply the number of items, since each item is very different. It's not like we have 3 wolves. This is a problem people sometimes make when modelling the jealous husbands. Although there are 4 wives and 4 husbands, each husband is different, so we can't just model the number of husbands. So instead, let's have 2 sets containing the elements on one side and the elements on the other. And that's fine, but we also need to add something to show where the boat is. And the way we're going to generate more states, we're going to first consider which side the boat is on. So that's the only side we can move from. And we're going to consider each item in turn, putting it in the boat and moving it. If that leaves a forbidden combination, we scrap it, otherwise we add that to our diagram. Now have a look at this code and see if you can see why it doesn't work. Pause to think about it. Well, we have correctly moved the boat across and the goats, and we've generated that new state, but now when we consider the next item, we're considering the new state rather than the old state. So that's not going to work. Instead, we're going to duplicate our current state each time we consider a new item and move the item and the boat to the other side. And if the constraints are not met, then we delete that set, which you can see we will delete these 2, leaving us with just this one. We can see how that's worked fine for the first one, but now we can also see I forgot to move just the boat. So that's why we need to make sure we step through the code when we write it, and we can very easily fix that, change the code, and see these extra 3 lines just say also duplicate the current state and move the boat and see if there are any constraints that are not met. We might also think how we identify states that were found before, because we need to make sure our graph doesn't keep generating new states if those states already exist. So we might have a string representing each state, for example, CW pipe BG and so on, and that will be unique for each state as long as we store them in order. So let's just step through this and see how it goes. The next option we've got is to move the boat back on its own. We could also move the boat and the goat back, but that would just take us back to the starting state. Next, we can move the boat with the goat or the boat with the wolf. Both of those are acceptable. Then we can move the boat back on its own. We can move the boat back with the cabbage and the boat back with the wolf. But some of these, well, this one here is going to be unacceptable, so we have to eliminate that one. Then from the state CBGW, we have 2 possible states, but this one is unacceptable. So we delete it. And you can see how this will unfold. I'm not going to generate the rest of them. Now, we will probably use BFS to generate the states, and we should also be checking for an end state. So let's pop a line into the code here. I've put if we found the end state, which would be what you can see there, then stop. In reality, it probably wouldn't be stop. It might be work out how to get from that state to the original state, or count the number of moves, or something like that. Now, I couldn't make a video like this without chucking in a couple of XKCD comics, which you should all be watching so you can feel intelligent when you're doing algorithmics, highlighting the absurdity of some of the problems, and also mentioning that there are harder variants of this problem to solve. Next, we consider the water jug problem. Again, it's another classic. You have possibly heard of it before. Given a 3-litre jug and a 5-litre jug, we need to measure exactly 4 litres of water. You should Google Mathologer Die Hard for this particular one. First, let's consider how each state can be represented. This is quite straightforward. It could just be an array where the first element is the 3 litre jug and the second element is the 5 litre jug. So the numbers represent the amount of litres in each. And we've started here by having them both full. And we could start by emptying one or both jugs. We could also pour from one into the other. And if we run through the solution here, it gets a little bit more complicated. So we could go pour the 3 litres from the 3 litre bottle into the 5 litre bottle, or we could pour 3 of the litres from the 5 litre bottle into the 3 litre bottle, leaving 2 litres. So if we had to code this, let's look at this code. Hopefully this works. So for each state, we'd look at the jug and we'd say, well, if that jug has water, we could consider just emptying the jug. So we would create a new state and in that state, empty that jug. And then we'd say, if the other jug is not full, well, that means I can pour some water into it. So I would create a new state. The amount I'm going to transfer is going to be the largest of either the contents of the jug that I'm pouring from or the spare capacity of the other jug I'm pouring into. And of course, that shouldn't be the maximum, should it? That should be the minimum. Always worth reading the code over and over again, isn't it? Let's step through this and get some more solutions. And I will just take you through the one that I know works. Bear in mind, a lot of these will link up. For example, all of them, you could just empty both bottles and put them into the middle state. Although the way I wrote the code, you have to empty one bottle at a time. I won't add all those on, but let's just see how this works in case you can't figure out how to solve it yourself. Or we could empty the 3 litre. We can put the 2 litres into the 3 litres. We can then fill the 5 litres. We can then pour 1 litre from the 5 litres into the 3 litres, which had 2 litres in it, which means it now has 3, and we have 4 left in the 5 litre bottle. And then we really should empty the 3 litre bottle as well. So we just have 4 litres of water. Whew, wasn't that fun? Again, we need to have a unique identifier for each state, and we need to state how we will traverse the graph and either decide that no solution exists or how we will return it, whether it's how many moves or whatever. I will leave you to decide this, neither is particularly tricky. When we're solving these problems, be clear in your mind as to whether you are designing a graph or an ADT for one particular state or a graph to hold all states. This was relevant for the 2024 exam question involving turning dials. I strongly encourage you, pause the video now and try this question on your own, keeping in mind what I just said. Well, you had two options here. We could have had an undirected graph with nodes representing dials, edges between nodes where they are adjacent, and then there would be a node attribute saying which way the dial is facing. So we've got to make sure we include all the relevant information. The other option was a 3x3 matrix, and you could either record a direction indicator like 1, 2, 3, 90, 180, 270, 0, or whatever, as long as we are including all that information. 2 marks, which were probably not too hard to get. So this was about recording one particular state. The next question is about dealing with all of those states. Now, hopefully you have done this and you've paused it and tried it. Hopefully you've covered this material. If we have an unweighted graph, so all the edges have either no weight or the same weight, and we're looking for the shortest route, we should be using breadth first search from the starting node, which will stop and return at the first solution node. Let's read the question. What does it tell us to return? Is it the weight itself? No, it is the solution node that can be reached by turning the fewest dials. So we return that first solution node. It might have said return the distance. Final question for this one. Make sure you pause and have a think and have a go at writing it. So we would have to change the edge weights on this one, making the points for a quarter turn, half turn, etc. And then we would run Dijkstra, stopping as soon as the first solution node is made permanent. Now, and also returning that node. You could also have used Dijkstra for the previous one. That would still be correct, just be slightly overkill. It's a really good idea to see as many of these questions as possible. You can find them, a lot of problems can be solved with state graphs. There are lots of problems you can find in this book. If you have any questions, leave them in the comments.